And let's continue on chapter 7 on estimating sample size. This section will present methods for using sample means to make inference about the value of corresponding population means. So we're going to learn how to come up with margin error and a confidence interval. Okay. So the sample means x bar is the best point estimate of the population mean mu, assuming sample is a simple random sample. And we will learn how to use the sample data, construct a confidence interval for estimating the value of the population mean mu. And then we learn how to interpret those confidence intervals. We also will develop ability to determine sample size necessary to estimate the population mean. The procedure we use has a requirement that population is normally distributed. The first one is a sample is simple random sample. The second one is the population, either population is normally distributed or the sample size is equal to 30, greater than 30. Okay. Now the margin error formula for estimated mu when sigma are known. So when sigma are known, and typically we're going to use a critical t values. Okay, so margin error equal to critical t score t alpha over 2 times sample standard deviation. Then n represents sample size. And critical t value t alpha over 2 has n minus 1 degree of freedom. And we're going to find it in so here alpha is the complement of the confidence level. First one, let's get to know the student t distribution. So important properties about the student t distribution. So student t distribution is different. Typically different for different sample size. And we're going to see sample size equal to 3, sample size equal to 12. The student t distribution has a similar bell-shaped curve. That's a standard normal distribution, but it reflects a greater variability, meaning the standard deviation is greater than 1. Still, that is expected with the small samples. So student t distribution has a mean t equals 0, and also compared to the standard normal distribution, z equals 0. Very similar. The standard deviation of student t distribution varies with the sample size is usually greater than 1. Compared to the standard normal distribution, which sigma is equal to 1 always. So as the sample size n gets bigger, the student t distribution gets closer to normal distribution. Okay, so it's a very similar graph to the bell curve. As you can see, the blue bell curve represents the standard normal distribution. And student t distribution with n sample size equal 12 actually is closer to the standard normal distribution or the bell curve. Student t distribution sample size equal 3, very small from the bell curve. So as the sample size gets bigger and increases, then student t distribution gets closer to the normal distribution. If the distribution of the population is essentially normal, then distribution, we use the student t distribution, t value equal to sample mean, x bar is the sample mean, mu is the population mean, S is sample standard deviation, and n is the sample size. So this is essence. This formula is the essence of student t distribution for all sample size. I refer to student t distribution used to find the critical value t alpha over 2. So in order to find the critical value t alpha over 2, we need to know alpha and also degree of freedom, which is n minus 1, sample size minus 1. The number of degree of freedoms for collection of sample data is the number of sample values that can vary after certain restriction has been imposed on all data values. So using df to represent the degree of freedom. Degree of freedom equals sample size minus 1. So let's summarize all these notations. Mu is the population mean, x bar is the sample mean, S represents sample standard deviation, n represents sample size. E represents margin error, T alpha of 2 critical T value, just like a critical Z score, critical Z value. Very similar concept. Separating the area of alpha over 2 in the right tail of the T distribution. So again, similar bell curve, alpha over 2 here, alpha over 2 on the left tail. So Z T alpha over 2 is located on the right tail. Okay. And this is procedure to construct the confidence interval to estimate the population mean mu. So confidence interval for the estimate of population mean mu with sigma unknown. First of all, find the margin error using the formula critical t-score times sample standard deviation over square root of sample size. You find the critical t-score in table A3. I'm going to show you where the table A3 is. Degree of freedom equal n minus 1. So now let's go to table A3. So open the formula sheet. And table A3 is located after the table A2. So table A3, t distribution, critical t values. Right here, you need two things: area in two tails, also the degree of freedom. Then they will have intercept. Area in two tails usually is what we call alpha. Alright, degree of freedom, area in two tails give us intercept. The intercept is gonna be the critical t-score. For example, let's say degree of freedom equal to 10, area in two tails equal 0.05. So the critical t-score here will be 2.228. And that's how you find locate the critical t-score here from table A3. Okay. Then once you have a margin error, then using sample mean minus margin error, that's what we call a lower limit. And then sample mean plus margin error, that's upper limit. Okay, so now let's look at procedure for constructing a confidence interval for population mu when sigma is unknown. Verify that requirements are satisfied. Couple things. Sample is a simple random sample. Also, either the population is normally distributed or the sample size is bigger than 30. Second condition, either population normally distributed or sample size is greater than 30. And now use n minus 1 as degree of freedom. Refer to table A3. And the alpha is always given once you know the confidence level. And find the critical t-score corresponds to the desired confidence level. And evaluate the margin error using the formula margin error equal to critical t-score times sample standard deviation over square root of sample size. And then we construct a lower limit using sample mean minus margin error, sample mean plus margin error, and the population mean is located within the interval. And then after that, we run the resulting confidence interval limit to 3 significant digits. So let's take a look at example. A common claim that garlic lowers cholesterol levels. In a test of effectiveness of garlic, 49 subjects. Here, 49 subjects is sample size 49. Were treated with the doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol in milligram per deciliter have a mean of 0.4, so we get a sample mean equal to 0.4. And because it's a sample, so it's a sample mean, we also have sample standard deviation equal to 21.0. Okay. Now use the sample statistics. N equal 49, sample mean, standard deviation 21 to construct a 95% confidence interval, estimate of the mean net change in LDL cholesterol after garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So requirements are certified simple random sample. Although it doesn't say that population is normally distributed, but the sample size is 49 bigger than 30. So the requirements are satisfied. Check that first. 95% confidence level implies alpha equal to 5%, which is 0.05. And sample size is 49. Degree of freedom equal to 49 minus 1 equal 48. And if you go to the table A3, as you can see, there's no 48, exactly 48 here. We have 50 and 45. As you can see, 48 is close to 50. So according to this principle, so the degree of freedom equal 50, and the area in two tails alpha equal 0.05, and we have intercept which is 2.009. And that's the critical t-score we're looking for here. And go back, critical t-score equal to 2.09. So we get critical t-score here. And use critical t-score, sample standard deviation, and then sample size. We can find the margin error first. Equal T alpha over 2 times sample standard deviation over square root of sample size. So that's going to be 2.009 times 21.0 over square root of 40. The result should be, let's see, should be 6.00063. 6.063. Let's double check. 6.027. Okay, and that's the exact answer. We don't have to run it. And again, it's also 3 significant digits right here. So we know the margin error. Now using the sample mean and margin error, you can find the lower limit. You can find the upper limit. I just constructing the confidence interval, so 0.4 minus 6.027, that's lower limit. Upper limit is 0.4 plus 6.027. And let's see the lower limit, 0.4, 6.027, negative 5.627. That's lower limit. Upper limit is 6.427. So we are not 95% confidence that the confidence interval of negative 5.6 and then 6.4 actually does contain the true population mean with a 95% confidence. And because the confidence interval limit contains a value of 0, so it's very possible that the mean of change in LDL cholesterol is equal to 0, suggesting that garlic treatment does not affect the cholesterol level. So it does not appear that garlic treatment is effective in lowering cholesterol. All right. And then similarly, upper limit is equal to sample mean, adding margin error, and then adding lower limit is the sample mean minus margin error. Now again, we cancel the margin error, we get twice of the sample mean. Divide by 2, we get the sample mean. Okay, and then upper limit is sample mean, adding margin error, minus sample mean, minus margin error. If you expand it, you're gonna get sample mean plus margin error minus sample mean plus margin error. And again, we cancel the sample mean, we get twice of the margin error on top. Divide by 2, we get a margin error. So if you know the both lower limit, upper limit, you can find the sample mean, margin error pretty easily just using these two formulas. Now find the sample size of estimating population mean mu. Okay, so this comes from this margin error formula of C alpha over 2 when the sigma is known, right? When sigma is known and the sample size is greater than 30, we're using critical z-score. And from this formula, we can come up with a sample size. Very similarly, you just square both sides of the equation. So we get z alpha over 2 square times sigma square times square root n square. Okay, so we get E square equal to critical z-score square times sigma square over n square. Now if you want to solve for n, no, square root of n square becomes just n. This is just n, then we can solve for n from there. Okay, and then n is equal to, you can use proportion to solve this, and you get this. N equal to z alpha over 2, so n times e square equal to z alpha square times sigma square. Now n is equal to z alpha square times sigma square over e square, and we can pull out the square outside. Now we end up with the formula here. critical z alpha over 2 times sigma over margin error with a square bracket raised to the second power. Here mu is population mean, sigma is population standard deviation, x bar is the sample mean, e is the desired margin error, and z alpha of 2 critical z score. So with the algebra, simple algebra, you can derive the formula for estimating the sample size. So if the computed sample size n is not a whole number, then always run it up to next larger whole number, no matter what decimal it is, right? So for example, if you get 6.0125, you still run up to 7. If you have 6.975, you also run into 7. So run the rule for the sample size n. Always run up the next whole number, as long as it's a decimal number. So find the sample size n when sigma is unknown. Typically, we could estimating the population standard deviation using range over 4. Range is usually equal to maximum value minus minimum value, and maximum value equal to population mean plus 2 standard deviation. Minimum value equal to population mean minus 2 standard deviation. If you find a difference, you get 4 standard deviation. Range is equal to 4 standard deviation divided by 4 becomes standard deviation. So this is one way to estimating the population standard deviation. You can also start a sample collection process without knowing the sigma. Using the first several values, calculate sample standard deviation S, and use it to replace the sigma. Again, we assuming the sample is simple random sample. So estimated value of the sigma can then be improved to more sample data is obtained, and the sample size could be refined accordingly. So estimate of the value of the sigma by using the result of the sum. Similar earlier study, right? You can use somebody else study as long as it's similar. This third way to estimate the population standard deviation, given the condition that you don't have the entire population available. Assuming we want to estimate the mean IQ score for the population of statistics students. How many statistics students? So this question is how many, meaning we're looking for sample size n. Statistics student could be randomly selected IQ score if you want 95% confidence. That sample means within 3 IQ points of population mean. This sentence here, sample means within 3 IQ points of population mean, give us margin error, E. So E equal to 3. Okay. And we also know critical z-score. So according to 95% confidence, critical z-score equal to 1.96. So according to the formula for estimating sample size, n equal to c alpha over 2 times sigma over margin error. Okay, let's take a look at the sigma here. Probably it's omitted from the question. Let me check what a sigma is. Population standard deviation. I'm gonna pull back the sigma later on to the slide. See what a sigma is. Sigma is equal to 15. So here the sigma is unknown, but yeah, I'll put it back later on. Sigma equal 15. It wasn't indicating the question itself. So now we're plugging all the numbers into the formula, so we get a square critical z-score 1.96 times sigma 15 over 3 and square it. Let's see what that is. Turn out to be 96.04. Again, the random rule is always run up to 97. That means with a simple random sample of 97 statistic students, let me just add it to the question here. The population and the population standard deviation. It's 15. Okay. Now it will be proper question, and it turned out to be the simple randoms of 97. So these students will be able to have 95% confident that the sample means within 3 IQ points of true population review. This section presents a method for estimating population mean mu. In addition to knowing that we are given the population standard deviation. So this is the case when the population standard deviation is given. So that means we're using a critical z-score. So margin error equal to critical z-score times population standard deviation over square root of sample size. Okay, so now here let's learn how to construct a confidence interval for estimating the population mean mu with a sigma norm. Okay, so we still need to review the concept. Mu is population mean, x bar represents sample mean, sigma is population standard deviation, n is the number of sample values, or sample size, e is margin error, and c alpha of 2 is critical z-score, separating area alpha of 2 in the right tail of the standard normal distribution. So the requirement or the pre-existing condition to construct a confidence interval for estimating population mean, sigma given, the sample is a simple random sample, all samples have the same size, equal chance of being selected, the value of the population standard deviation is known, either one or both of these conditions satisfy the population is normally distributed, or the sample size is bigger than 30, then we can use the critical z-score here. So first of all, let's find the margin error using this formula: critical z-score times population standard deviation over square sample size. And from there, we get a lower limit and an upper limit. Lower limit is sample mean minus margin error. Upper limit is the sample mean adding margin error, and the population mean is located within the interval. You can also write it as x bar plus minus margin error or the interval rotation. Okay. So let's take a look at example. People have died in boat aircraft accidents because the absolute estimate of mean weight of man was used. In recent decades, the average weight of man has increased considerably. So we need to update our estimate of that mean so that boats, aircraft, elevators, or other such devices do not become dangerously overloaded. Use the weight of man from a random sample. We obtain this sample statistics for the simple random sample. Sample size equal 40, sample mean equal to 172.55. Research from several other resources suggests that the population weight of man has standard deviation given sigma equal 26 pounds. Now, first of all, find the best point estimate of the mean weight of the population of man. So sample mean equal 172.55 is the best point estimate of a population mean, since the sample is a simple random sample. Then the second step, construct a 95% confidence interval estimate of the mean weight of all men. What do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger composite water vessel in 1960 as given in the National Transportation Safety Board Safety Recommendation M-04-04. So the sample mean given, we also know the sample size is 40, and the sample mean is the best point estimate population mean mu. So now 95% confidence interval implies alpha equal to 0.05, a critical z-score from table A2 equal 1.96. Now calculate the margin error, critical z-score times population standard deviation over square root of sample size. So sample size here turned out to be 40. Okay, population standard deviation equal 26 pound. So we have that sigma 26, sample size equal 40. Now let's throw in all the numbers. 1.96 times 26 over square root of 40, and let's run it to 3 significant digits. 96 times 26 divided by square root of 40. So now it'll be 8.057 approximately. Okay, so we get a margin error. Now let's construct a 95% confidence interval. Sample mean minus margin error, lower limit. Sample mean plus margin error, upper limit. Sample mean is 172.55. So using 172.55 minus 8.057, lower limit. Upper limit adding the sample mean by the margin error. Okay, let's see what's the lower limit was. Minus 8.057, 164.493. The unit is pound. Sample upper limit adding them get 180.607. Pounds. Okay, so this is 95% confidence interval. Now based on the confidence interval, it is possible that the mean weight 166.3 used in 1960 could be used in the mean weight of man today. However, the best point estimate of 172.55 indicates we should probably use this instead, because it's much greater than 166.3 pounds back in the old day. Considering that the underestimate of the mean weight of man could result in lives lost through overload boats and aircraft, so these results strongly suggest that additional data should be collected. Probably conduct a new research study, come up with a survey or a poll, get the data, sample data, and analyze one more time. And this flow chart shows you what kind of either t distribution or z distribution to use. So if sigma known and the population is normally distributed, or the sample size is greater than 30, we use z distribution, normal distribution. If sigma unknown and the population is normally distributed and the sample size is greater than 30, we use student t distribution typically. If population is not normally distributed or sample size less equal to 30, then we use non-parametric method of bootstrapping to conduct confidence interval. That's pretty much